Okay, so the problem we're looking at today is the USACO 2021 February contest gold problem 1 of Stone Game. So you can pause the video first and look at the problem yourself. Okay, I assume you read through the problem. So basically, this problem is you have two cows, Bessie and Elsie, playing a game with m piles of stones, and each time they each taking turns removing stones from these piles, where the stones removed on the SI+1's turn has to divide the stones removed on the turn after it. So if you remove FSI on I turn and then you remove SI+1 on the I+1's one, then SI have to divide SI+1. And now the first cow who's unable to move the stone on her turn loses. And now you're Bessie who moves first, and you're trying to compute the number of ways that she can make her first turn in order to guarantee a win. And two ways considered different if you either remove different number of stones from the same pile or you remove stones from different piles. So now you can think about this problem yourself first. Okay, I assume you thought about this problem. So first of all, I would say I really like this problem. It's one of those USACO problems where I feel like this should be more silver, but because it doesn't have much algorithm, but the difficulty is just right for gold, I would say still, because there's not really that much coding and debugging of this code. As long as you can come up with the algorithm, is just really short and simple coding. So first of all, let's draw a graph for this problem right here. So now, since we're trying to determine for how many ways Bessie can make her first move, we can assume first if Bessie makes her first move by removing S stones from some pile. So removing S stones from some of the piles, and now we can divide the piles into sections of S, right? And ignoring all the green parts. So the green parts are the parts where you have remainders, and we just ignore them because if you have a pile of less than S, meaning like if you remove S from this pile, then obviously the green part is not going to be removable. So we just ignore them. So now we have piles like this, right? So the first observation that we can make is when the last round we removed X, when we removed X from last round, we can ignore the green parts, right? That's obvious. And the second observation is the most important one, in which we notice that after dividing them into parts of S, and then we shrink them, we define their size as how many S they contain. So size of the first one is 2, second one is 4, right? 4, 1, 2, right? That's obvious. And now, if we have some quantity if we have all quantity occurring in these piles of stones all even number of times, that means the second player to move is guaranteed to win. Because think about it, if you have, let's say, if we get rid of this tower, and now we have all quantities of, after dividing into S, groups of S, we have all of them, all of the sides of the tower, the quantities occurring even numbers of times, if you know what I mean, right? Because we have 4 occurring twice, we have 2 occurring twice, and now the cow that makes the second move is guaranteed to win. Why? Because they can just copy the move of the first cow. If the first cow, say, take S from this tower, then she can take S from this tower because they have the same height. They're basically identical. So she can keep copying moves of the first cow until there's nothing left and the first cow can't make another move and the second cow automatically wins. So this is the key observation for this problem. If for every quantity, for every size of the tower after dividing by S, if every quantity occurs an even number of times, then the second cow to make a move is guaranteed to win. So with that observation, we can now start caseworking our ways through this problem, right? Because that observation makes everything much easier. So here's my code. I wrote down all the solutions as comments in the front of before the code. So first of all, the first observation, obviously, we can just divide the towers into sizes, into chunks of S, and find that as their size, right? And the second key observation is the one that I just stated, in which if you have even number for every A, then obviously the second cow to make a move will win. And now the third observation is also very important. However, it's gonna be easier to come up with after you reach the conclusion of the second observation. So what the third observation states is we only want to perform operations on A's, and now the A's that we state here is the A's after dividing them into chunks of S, right? We only want to perform observations on A's with odd occurrence. Because think about it, if we perform one on even occurrences, obviously we can't pose direct threat to our opponent because they can just copy our move always if the tower that we perform moves on have even numbers of occurrence, right? So we can't pose any direct threat. And if first of all, if there's another tower with odd numbers of occurrence, the other cow can just simply remove the a with the maximum a with odd numbers of occurrence, right? Because then we will be left with all evens, and we can't remove any of the smaller odd number ones because they're already ignored as the opponent removed the s of higher. You have to make sure your next s divides this previous s, right? So basically you're cooked if you touch any even tower. You can only perform moves on odd tower, and exactly why is explained here. I'm not going to read the whole thing. So that's the second observation. Now we can do casework. So what are three situations? First of all, if there's only one a with odd occurrence, and then the a we're talking about still after dividing into chunks of s. If there's only one of them with odd occurrence, we notice that this a has to be 1. Because if it's not 1, after we remove s from this a, let me pull out my drawing again. If this a with odd occurrence, let's say this tower doesn't exist, right? And now we have 4 having odd occurrence after removing one s, and now the a minus 1 will also have an odd numbers of occurrence, because think about it. Now we have 0 4s, which is even now, obviously, but we have 1 3s. 1 is odd, right? And now the opponent can just remove this 3, and now we're cooked. So when there's only one a with odd occurrence, it has to be 1. Otherwise, there's no way we can win. And what if there's 2 with odd occurrence? Well, let me try the drawing again. If there's 2 with odd occurrence, in which let's cross out this tower and let's cross out. No, we don't need to cross out anymore. So we have this one and this one. So now, if if we remove the smaller one of the 2, then obviously the other team can just remove the bigger one, and then we're cooked, right? Because now we're left with all even. Because every quantity of a above this bigger one is even. So now after they remove it, we're cooked. So we can't touch the smaller one. And what if we do the bigger one? Well, we do the bigger one. Sometimes it works. If the bigger one with the odd occurrence is just exactly 1 above the smaller one, so meaning if 2 has odd occurrence and 1 have odd occurrence, then after removing 1 from the 2, now we have 0 for 2, right? And then we have 2 for 1, which both are even. And now the other team is cooked because everything else we assume is also even, right? However, if we have the case that we just used as example earlier, if we have 4 having odd occurrence and 1 having odd occurrence, there's no way that we can win this. Because if we remove 4, and then 3 would have an odd number of occurrence, and if we remove 1, obviously, as we discussed, it would not work. So basically, if we have 2 with odd occurrence, they have to be next to each other, and then we can only remove the top one. And what if we have more than 2? Well, it's obvious that we can't remove all odd if we have more than 2 with odd occurrence, so you're cooked, basically. And now after those analysis, we have a basic idea of the algorithm. We can enumerate what s we use for the first move, like how many stones we remove from any pile on the first move. And then according to these caseworks, we can first of all, of course, we can recompute the a by dividing them into chunks of s, and then counting which a's have odd occurrence. And if first of all, if there's more than 2, we're cooked. This s doesn't work. If there's exactly 1, we check if it's the first one. And if there's exactly 2, we check if they're next to each other. And if one of these 2 hold true, well, then this s works. But this problem is not asking for which first move quantity works. It's asking for how many ways we can move first. And moving from different towers also counts as different ways. So that's also easily solvable now that we know which ones work. So when there's only 1 with odd occurrence, obviously however many towers have that quantity is going to be however many towers we can choose to remove from. And if there's 2, however many towers with the higher of the quantity, in which is the one that we want to remove from, is the towers that we can choose to remove from. So this is my code is really simple. That's why I like this problem a lot. So of course we pre-process a prefix sum in order to find because we can't actually compute out the a after dividing into chunks of s. So we just count out how many a's are between s and s times 2, how many are between s times 2 and s times 3, and we use prefix sum to do so. Every time num is the number of a's between j and the next multiple of I, right? J is just every multiple of I below the max value of ai. And now count is the number of odd occurrence so far. If there's more than 2, obviously we just break, and then we go to the next S because this S doesn't work. If it's 1, we record down the first index of odd occurrence. If it's 2, we record down the second index. And now if it's first one, we check whether it's the first. If the J over I is 1, meaning after dividing into chunks of S, there's only one chunk. Well, then we the answer is plus by however many towers have that quantity, because we can remove S from any of these towers. And if count is exactly 2, then we have to check if the 2 are exactly next to each other. As we have proved above, that is the only case in which when there's 2 quantity with odd occurrence, that's the only case that we can still guarantee a win. So then we can remove from any towers with the higher of the occurrence, which is second plus 1, which is second. And now we just use the prefix sum to count how many are between second plus 1 minus 1 and second times I minus 1. Okay, and that's the answer. So now we can come back to the question today, and we can see that this problem is really good because there's a lot of thinking and not much coding, and it's also a lot of fun, I would say. And I think this is what a proper silver problem would actually look like. Because gold, you will want to include a few more algorithms, but for silver problems, I think this is like the right type. Not the right difficulty, of course. This is a bit too difficult for silver problems, but I think it should involve more thinking than coding, because I suck at debugging, and debugging is very, very annoying. And this code will be posted down in the comments, and I did comment in the code of the bugs that I make, which if you read through the code, you'll see that they're really, really stupid. So yeah, even for a simple program like this, I made mistakes. So that's why I think for silver, you should make the coding less complicated and the thinking more fun. Okay, so I hope this video helped. Thank you for watching.